atomic structure, we're going to look at what the numbers on the periodic table that you might see mean and how the top number can be different, or the largest number can be different. We're going to look a bit about what that means if that number's different, and we're going to start talking about radioactivity in more detail. So we're going to get you to understand really what radioactivity is and how it works. This is linked to the AQA specification, but it kind of works for most GCSE radioactivity sections. I will be giving you more information than you probably need, but what I want you to do is really understand what's happening rather than just giving you the facts. So I'm going to kind of build the story up, but from the bottom, rather than just jump in with the facts and expect you to kind of understand how it works. So we're going to build a firm basis for that. So let's start with what's going on here. What does this mean? In your periodic table, you will see a number of elements. You'll be good at this in chemistry. In physics, we have to cover it because we're interested really in what's going on in the nucleus. But here we've got lithium, two numbers, 7, 3. Some periodic tables, and mostly in chemistry, you will see the 3 at the top and the 7 at the bottom. In physics, the general pattern is to put the larger number at the top. What do these numbers mean? The top number we call the atomic mass. So this number here is the atomic mass, and it tells us something about the element. It tells us something about what that atom looks like. And if you remember last session, we looked at what the atom looked like. We looked at the structure, the fact that there was a nucleus, and inside the nucleus we had protons and neutrons, and around the outside in shells we had electrons. The bottom number is called the mass number, and that's the smaller number. The atomic mass tells us the number of protons plus neutrons in the atom. So it tells us how many particles are in the middle of the atom, in the nucleus. So this here is our nucleus, here are our protons and neutrons. The bottom number tells us the number of protons. It tells us how many of those particles, those protons and neutrons, are actually just protons. So this is the mass number, and it gives us the protons. So let's colour some protons in just so you can see. So using the periodic table, we can now get a really good idea of what those atoms look like. What do the atoms actually look like? And you will be expected in your exam to be able to describe an atom from these two numbers. So let's have a quick look at what that means in terms of a question. It's rare. It's rare that you'll get a question saying draw the structure of the atom, but let's make sure you can do it just in case. So if we take the example of lithium that I used before, lithium 7, 3, remind yourselves again, the 7 tells us the number of protons and neutrons, and the 3 tells us the number of protons. So this is the total number of particles in the nucleus. So if we were going to draw it, here's our lithium, we'd have 7 particles in the nucleus. 3 of those particles we would label protons. The remaining particles we would label neutrons. So this tells us now that this atom here has 3 protons and 4 neutrons, adding up to 7, which is the mass number. It's where the mass is. And if you remember, we said that the protons and the neutrons were the ones that had the mass. Remember that when we've got an atom that's not charged, the protons and neutrons are the same. So this also tells, the protons and the electrons are the same. So this also tells us the number of electrons in this atom. So if we remember how we fill our electron shells from chemistry, we know that we've got 2 electrons on the first shell and we've got 1 electron on the second shell. So here we've got a really nice picture of that lithium atom, going back to our work that we did last week, looking at the structure of the atom. So in the middle we've got 7 particles. Of those 7 particles, or subatomic particles we can call them if we want to be really precise, of those 7 particles we know 3 are protons, Therefore, the remaining 4 must be neutrons. If this atom is uncharged, then the number of electrons is the same as the number of protons, and it will be 3. Of course, not all atoms are uncharged. Atoms lose and gain electrons, and that's a lot of chemistry. Chemistry are really interested in that. Remember, if you lose an electron, the atom becomes ionized. If you lose an electron, and if you lose an electron, overall we've got more protons than electrons in the whole atom, so we can say that that atom is now a positive ion. We've got more protons than we have electrons. It's also possible to gain an electron, and then of course we would have a negative ion. But we're not really interested in that. That's much more in the realms of chemistry, but it's important to understand that you can gain and lose electrons, so that might not always be the same as the number of electrons, but if you do, then we produce an ion. If you lose an electron, it's positive because we've got more protons than we have electrons. If you gain an electron, it's negative because we've got more electrons than we've got protons. So that's how we use that. Make sure that you can interpret that. Make sure that you know that this means the number of protons and neutrons, and this means the number of protons. So that's fairly straightforward. If you want to have a practice, see if you can draw the atomic structure for various different atoms. Should we have a practice now? Let's have a go. So let's have a look at carbon 12(6). Let's see if we can remember, or we know how to interpret those. Let's have a look at nitrogen 14(7). What do those two things mean? Well, what we want to know is how many protons we've got in there, how many neutrons, and how many electrons. So let's have a look. Protons, neutrons, electrons. So the top number tells us that there are 12 particles in the middle for carbon. It tells us that 6 of those particles, or those subatomic particles, are protons. So we've got 6 for the number of protons. If we've got a total number of 12, 12 minus 6 means that we've got 6 neutrons. And because all these two atoms are uncharged, we know that we'll have 6 electrons. So let's go back and have a look at that first. It tells us that there are 12 particles in the middle, 6 of which are protons, so we can fill in the protons straight away. 12 minus 6 gives us 6 for the number of neutrons, and because it's uncharged, the protons and the electrons are the same. Have a go at nitrogen yourselves. How does that work? See if you can think it through. What does that tell us? What does that tell us? What can we fill in first from there? Hopefully you've got it. Hopefully the first thing you thought about was that you could put 7 protons in there. That means that we've got 7 neutrons, because 14 minus 7 is 7. And because it's charged, we've got 7 electrons. Remember that there are not always the same number of protons and neutrons. Many elements don't have anywhere near the same number. It just happens that those two do. So don't worry if the protons and the neutrons aren't the same. If we go back to lithium that we looked at before, we had lithium 7(3). Here we knew we had 3 protons, we had 4 neutrons, and we had 3 electrons. So these numbers do not always have to be the same. But remember, if it's not an ionised atom, and you will rarely in physics find anything that is ionised, then these two numbers will be the same. Okay, so how else can those numbers be different? Those numbers can be different if you let's have a look for a minute at what happens. So we've got something like oxygen, 16, 8. We've got something like carbon, 12, 6. The proton number is the number that defines the element. If you change the proton number, you've got a different element. Proton number gives all the properties of that element. So it's the proton number that tells you which element it is. The number of neutrons in an element can change. And for example, carbon, you can get carbon with 13, 6, and you can get carbon with 14, 6. You can get oxygen, 18, 8. What's gone on here? Whoops, I've written carbon and it should be oxygen. What's gone on here? What we've got here is extra neutrons in the nucleus. And many elements exist with extra neutrons in the nucleus. So you'll have 8 protons and 8 neutrons here. But for this one, we've got 8 protons and 10 neutrons in there, because remember that this is the protons, this is the neutrons plus protons. So this tells us that 18 minus 8 gives us 10 neutrons. Here we've got simple, straightforward, 6 protons, 6 neutrons. Here we've got an extra proton, here we've got, an extra neutron, here we've got an extra 2 neutrons. So we can have elements that still exist. So carbon can exist in 3 different forms, or more than 3 different forms, with different numbers of neutrons. So can oxygen, many, many elements. Chlorine is another really common one, hydrogen similarly. So what does it mean to have these extra numbers of neutrons? We call these elements, or these variations in this same element, we call them isotopes. Iso meaning the same. So oxygen 18 is an isotope of oxygen 16. It's got 2 extra neutrons. It behaves in exactly the same way. It's got the same melting point, the same boiling point. All its properties are the same. The only difference is that it's heavier. So it's really difficult to separate isotopes. Here we've got 3 isotopes of carbon. Carbon 12, carbon 13 and carbon 14. Carbon 14 of course is heavier than carbon 12, but that's the only difference. So the only difference between that is that they're heavier. The ones with the more neutrons are heavier than the ones with fewer neutrons. And you just really need to understand what an isotope is. In a question it might give you something like these 2 isotopes of oxygen and ask you to say what they are. So you would say these are 2 isotopes for the mark of oxygen. So that's all we're going to do really on atomic structure. Now we're going to move on to the cool bit, the more interesting bit. We're going to talk a bit about radioactivity. So what I'm going to do is I'm going to go from the real basics of this. Some of this is quite complicated. Don't worry if you don't understand it. Play the video back and see if you can pick it up. If you can't, email me on Google Classroom and I'll do some work with you to make sure you do. So let's think about our atoms. Let's think about our matter. So here's our nucleus with our protons and our neutrons inside it. It can be any element. You can work out which one it is if I put the letters in. I'm putting them like that. Doesn't matter how they'll be arranged. So here's our atomic nucleus. We're now going to dump electrons. We're going to lose the electrons and we're going to talk only about nucleus even. Okay, so here's our nucleus. As we've already said, some nuclei have more neutrons than protons. If we were to take every atom, look at every nucleus, if we looked at the number of neutrons and the number of protons, what we would find is that as the number of protons went up, the number of neutrons went up. So as you got more protons in your nucleus, generally, with the elements that exist, there are more neutrons. Make sense? As you get more protons, you're likely to get more neutrons. And as that nucleus gets bigger and bigger and bigger, we get increasingly more protons, almost to sort of pad it out. There's the 1-to-1 line, where you've got the same number of protons and neutrons. Here, this is what exists in reality. We have more and more neutrons. And we call this line the line of stability. We say that any element with a nucleus that has the number of protons and neutrons that sit on this line is stable. It's not going to change. It just sits there, carries on as it is totally stable. Nothing's going to happen to it. Nothing's going to change. And most of our elements that we know sit on this line of stability. However, we also have some elements that sit outside this line. Often they're isotopes, but they sit off this line of stability. They sit elsewhere. That tells us that the nucleus is unstable. There's too much in the nucleus to balance what's going on in there. The forces in the nucleus aren't enough to hold that nucleus stably in place. So what happens is it changes. It can't remain like this. And we're going to talk now about how that nucleus changes and moves towards this line of stability. So let's go back for a minute and recap what we said. So here's the nucleus that we talked about before. We know that it's got neutrons and we know that it's got protons in. And we know it's stuffed full of neutrons and protons. Okay. When we look at the nuclei that we know, of the elements that we know, and we plot the protons and neutrons on a graph, if we plot the number of protons and neutrons, we get this line that starts off pretty much 1-to-1 and then curves up a little bit. And most stable elements sit on this line. They have a number of protons and neutrons that sit on this line. Small elements have the same number of protons and neutrons. As you get bigger and bigger and bigger, you get increasingly more neutrons in there to keep that nucleus stable. If you think the protons are sort of, a way of thinking about it is that the protons are positive and they're trying to kind of repel out of there. So you need increasingly more neutrons to balance that kind of push out. So that's what we mean by the line of stability. But in the real world, we get these weird elements that exist around here, and many of them are isotopes. And they are not stable. They will not stay like that. They could stay like that for a long, long time, but they will not remain like that forever. And we'll talk about how long they stay like that in a bit. But let's look at what happens here. How does that work? How do they get more stable? What happens? So now we're going to, let's get this in my face. Now we're going to look at radioactivity. So there are three ways really that this atom can get more stable. Two main ways that we need to look at. So here's our atom. It's too full. It's got too much stuff in it. Okay? And it needs to lose or dump some of these protons and neutrons in order to move towards that line of stability and get more stable. So what happens? There are three ways. I'm going to talk mostly about two today. There are three ways that atoms can lose particles in order to get more stable. And those are, we're going to talk about them now. The first one we call alpha decay. The second one we call beta decay. And there are two types of beta decay. We're only going to talk about beta minus decay today. Also, so these are the three, 1, 2, and then there's also beta plus decay, which we're not going to talk about. They're the two ways atoms can lose particles, or nuclei can lose particles to become more stable. Also, nuclei will lose energy to become more stable, and we call that gamma And you remember we've met gamma radiation in our in the electromagnetic spectrum in the waves section of the syllabus, and we'll talk a little bit about that, but we're really going to focus on these two today. So how does it work? Here's our nucleus, way too many protons and neutrons. What can happen is that nucleus can lose groups of particles. Now, this nucleus, remember, I've only got a few protons and neutrons in here. Remember that inside a nucleus we've got many, many, many more protons and neutrons. But here, this atom, this nucleus, can lose particles only in groups. It can only lose it in terms of 2 protons plus 2 neutrons. That's the group that can be spat out of the nucleus. So there's, if you think of the nucleus, really, really stuffed full of protons and neutrons. And what happens is it's not got enough energy, think of it as energy, to keep that nucleus together. So particles get spat out of it, spat out of the nucleus. And they're spat out in groups of 2 protons and 2 neutrons. And we call that alpha decay. The 2 protons and 2 neutrons together are called an alpha particle. So this is an alpha particle. And if you think about this nucleus now with many, 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 many protons and neutrons in there, as that decays, it loses groups of 4 particles, 2 protons and 2 neutrons. They're spat out of the nucleus as alpha particles. So this leaves the nucleus. What does that mean to the particle? Let's have a look at something like uranium. Let's have a look at uranium. Let's have a look at uranium-235-92. So here's our uranium. We're going to say it's got 235 particles in the nucleus, 92 of which are protons. Makes sense? Remember what we did just before. Let's look at what happens when it has one single alpha decay. So here it goes. It loses these 2 protons and 2 neutrons. Now that alpha particle is actually a helium nucleus. If you look on your periodic table, you will see that helium looks like that, 4 particles, 2 of which are protons. So an alpha particle is actually a helium nucleus. So let's have a look at the decay of this uranium. Uranium-235-92 is going to decay. It's unstable. Let's say it's unstable and it's going to decay. It's going to move. It's going to lose a 4-2 helium nucleus. And what's left is another element. And we're just going to call it X for now, because I just want you to understand the process. So let's call it element X. And what have we got left for element X? Well, we start off with 235 and we're going to lose 4. So we're going to have 231 left. We're going to start off with 92 and we're going to lose 2 and we're going to go to 90. So element X is 23190, and you can have a look and in your periodic table and look up what the element with the atomic number 90 is, or 90 protons, and you'll be able to fill that in. So let's go through that again, because that's a little bit more complicated, and instead of putting uranium on there, I'm just going to do a general equation. So alpha decay happens when we've got an unstable element. It's unstable, it's not sitting on that line of stability, it's got the wrong number of protons and neutrons, and it needs to lose protons and neutrons in order to get more stable. And the only way an element that decays by alpha can get more stable is to spit out these groups of 4 particles 2 protons and 2 neutrons that we call an alpha particle, which is a helium-42 nucleus. Okay? Are you with me? So unstable, it's going to needs to lose some particles. It's going to lose 4 particles at a time. We call that an alpha particle, which is in fact a 4-2 helium nucleus. So if we start off with element Y, and we're going to lose a 4-2 helium nucleus, we're going to end up with element X. The element's not going to stay the same because we've lost 2 protons. So if we start off with element Y with a mass number A and an atomic number Z, we're going to end up with element X with A minus 4, Z minus 2. And that's the generic or the general equation for alpha decay. Start off with element Y, atomic mass number A, atomic number Z. We're going to lose 4 particles, which gives us A minus 4. We're going to lose 2 particles here, which gives us Z minus 2. So that's alpha decay, and that's how that works in terms of that nucleus. And if you think of something with a huge number of protons and neutrons in the nucleus, the element can keep kicking out alpha particles, and it will change to different elements as it moves on. So we always thought that elements were fixed and they couldn't change, but actually if they are unstable or radioactive, then they can change. And I just want to talk, before I go on to beta decay, a little bit about how we can predict what happens here. How do we control this kind of stuff? What's it all about? Because these alpha particles are not the sort of things we want hanging around, and I'll explain to you why they're not the sort of things we want hanging around in a bit. But let's talk for a minute about whether we can control it. And the point is that you cannot control this. You can't predict when it's going to happen. You can't predict when an alpha particle is going to be ejected from the nucleus. You can't predict which particles are going to be ejected from the nucleus. We say that this radioactive decay, and we call this decay because this nucleus has decayed into this nucleus by giving out an alpha particle. And we say radioactive decay is random and spontaneous. So it happens all by itself. You can't control it and you can't predict. So I've seen exam questions that ask you what random and spontaneous mean. It means that you cannot predict which particle will decay or when. The other thing to remember is that you can't control this. You can't change the temperature. You can't up the temperature to make it go faster and reduce the temperature. You can't change the pressure. There's nothing that you can do to control it. Once you've got a radioactive element, it is going to carry on decaying by itself and there is nothing you can do to stop it. Okay, so that's alpha decay. Let's talk about beta decay now. Now beta decay is a bit more complicated. So make sure you've got alpha decay in your head. So alpha works because we're losing particles from the nucleus and we're losing them in groups of 4. And those groups of 4 we're calling alpha particles, and they are in fact helium nuclei. They've got 4 groups of 4 particles, 2 of which are protons and 2 of which are neutrons. Okay, so let's look at beta. Beta's a bit different. How does beta work? So here's our nucleus. Let's go back to our unstable nucleus with its protons and neutrons sitting in there. Doesn't matter how many we've got, let's put a few in. We'll give it an extra neutron. Okay, So this element isn't going to decay by alpha. The way this element decays is by beta. So we're going to talk about beta decay. So it's a different element. And this element we call a beta emitter. It gives out beta particles, or it's a beta decay. And a beta particle is an electron, E minus. It's just an electron. And I can hear those of you that have got your head around the structure of the atom and thinking you've got it all understood. You're thinking, well, how do we get an electron out of that nucleus? How on earth do we get an electron from there? We've got no electrons in there. The electrons are around the outside, and I've already said we're not interested in what's going on around the outside. So how we get an electron out of that nucleus is like this. Neutrons are not always stable, and neutrons can break down to produce a proton and an electron. So in this unstable nucleus, instead of kicking out 4 particles as an alpha particle, it does something different. The neutron now breaks down. The neutron breaks down, so let's break this neutron down here. So this neutron is now going to be the one that breaks down. It turns into a proton and an electron, so it's going to do that. The electron is going to be kicked out really, really fast. So there's the electron. It's going to go out close to the speed of light. And this is now changed into a proton. You get some weird energy out of that, which is called an antineutrino, and I'll show you how that works in the equation, but don't worry too much about that. It's just to make sure you get the full picture. So beta decay is different from alpha decay. We're not losing groups of protons and neutrons as alpha particles. This time what's happening in the nucleus is the neutron, which is unstable in the nucleus, breaks down to produce a proton and an electron, and the electron is kicked out of the nucleus. So what you've got now is a nucleus with 1 extra proton. So how does that work in terms of decay? Let's have a look at what happens if we, to the equation, if we want to show the decay of beta. So here's our original, let's call it element X, and it's got A particles in the middle, protons plus neutrons, Z protons. And it's going to decay by beta. So we know that it's kicked out an electron, and we're going to call that 0 minus 1. We say that the electron is minus 1 proton. Don't worry too much about that. You'll see why it's there to balance the equation in a minute, but that's how you write beta decay in an equation. So beta, it's decayed by beta, it's lost an electron, and what's happened to the element? It's gone into element Y because it's changed the number of protons, and the number of protons has gone up by Z plus 1. Did we change the number of particles in the middle? No. So A stays the same. So let's have a look at that again. In our original element with beta decay, we've got Z, the number of protons. We know we've got Z, the number of protons, and we've got A, the number of neutrons. We know that 1 neutron breaks down to produce a proton and an electron. Remember that? And the electron is kicked out. The electron is the beta particle. It's the particle that decays. So the electron is kicked out of the nucleus. That leaves you with a nucleus. Let's draw it. Put 8 in there. Proton, 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 neutron, 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 neutron. So here's our neutron. It's broken down to produce a proton and an electron. So it's gone to, here's our electron, and here's our element that's left. We've now lost that, so I've got 2, 3 at the top, 2, and then 1, 2, 3 at the bottom, 3 at the bottom, and one of these is now a proton. So neutron, 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 proton, proton, proton. So there you go, that's what's happened. So here's our original nucleus, 1, 2, 3 protons, 1, 2, 3, 4, 5 neutrons. We've lost one of these neutrons and it's become a proton. So now we've got 4 protons in the remaining nucleus. We've now got 4 neutrons because we've lost that neutron. So the number of particles in here hasn't changed, but the number of protons has gone up by 1. So in beta decay, that's what's happened there. So in beta decay, we lose a neutron, which doesn't change anything in terms of the number of particles there. But that neutron turns into a proton and an electron. There's the electron, and we add the proton to the bottom. Make sure you can do those equations. What could they ask you? Commonly, students are unable to do those equations. It's not, you will have just, if you understand it, that's great. If you understand if you know and learn what an alpha particle is, so an alpha particle is a helium nucleus, and you know and learn what a beta particle is, you're half the way there. Remember that all equations have to balance. So you've got the element that they've given you, any element, AZ. You're saying, they're asking you to do alpha decay. So what you're going to do is you're going to say, okay, I know that's a 4,2 helium nucleus, so I can put that in. So what am I going to be left with? I'm going to be left with another element, element Y. And it's going to be, this side of the equation has to balance this side of the equation. So this, of course, is going to be A minus 4, and this is going to be Z minus 2. Does that make sense? So it's not that hard. As long as you know what an alpha particle is, you can get the equation. Similarly, with a beta particle, it's a little bit more difficult because you've got another step in there. So the question, if they're going to ask you to do an equation for beta, will be a bit harder. It'll be more marks. It'll either be more marks or it'll be a higher level question. If we've got a beta decayer with AZ, we know that we're going to give out an electron. And remember, we write it as 0 minus 1. And we're going to end up with another element, Y. So once we know what our beta particle is, A, here we've got nothing lost from the A, so A stays the same. We've lost one here, so this is going to be Z plus 1. So Z plus 1 minus 1 gives us Z. So that's why that works in that equation. So as long as you know that an alpha particle is a 4,2 helium nucleus, and you know that a beta particle is written as 0 minus 1 electron, you can do any equation. You don't need a huge amount of knowledge there. You just need to remember those two and think about the equation. Think about the fact that you start with one nucleus and it's going to decay into another nucleus, giving off one of these two particles. So you don't worry too much. Have a practice, have a look at what might happen with some elements. I'm sure there's plenty in your revision guide. If not, I'll put some, give me a shout and I'll put some on for you to practice. Okay, so that's what's happened with those two equations. What else could they ask you? The other tricky question they ask you with this one is what does the nucleus look like after alpha or beta decay? So rather than getting you to do the equation, and I would say probably 20–30% of students can write the equation and write the equation correctly. Often you get a mark just for writing helium 4,2 or 0 minus 1 electron, so it's often 2 or 3 marks, but many students don't get that right. And the next one that students really fall down on is, and they ask you, what is the difference between the nucleus before and after alpha or beta decay? So what does the nucleus look like afterwards? So what is different about the nucleus after, and we'll talk about, so alpha or beta decay. Just as an aside, the symbol for alpha is the alpha there, and the symbol for beta looks like that. So we'll use those shorthand from now on. So alpha, here is the alpha symbol, beta. So what does the nucleus look like? How do you answer that? For alpha decay, you would say the nucleus has 2 fewer protons and 2 fewer neutrons. Don't say it has 2 fewer protons and neutrons. You won't get the marks. You've got to be really clear about where you put your comma if you're going to do that. So you're going to have, say, 2 less or 2 fewer protons, 2 fewer neutrons. That's for alpha. That's the answer to the alpha decay question, 2 marks. And for the beta decay question on that, it would be the same number of particles one more proton, 1 more neutron. This is the crux of it, 1 more proton and 1 more neutron, but I've seen questions where they want students to say that the number of particles hasn't changed as well. So what have we done? We've talked about what alpha and beta are. We've talked about unstable nuclei. We've talked about the fact that you can't control what happens. And we've talked about the fact that they're trying to move towards that line of stability. Let's go back and see if we can now look at what we've talked about in terms of alpha and beta decay and see how that moves towards the line of stability. Then I'm going to go back to the beta decay equation and just add something to it for you. So remember we had the number of protons here and the number of neutrons here, and we had the line moving up like that. With alpha decay, we've said that we lose 2 protons and 2 neutrons. So if we're going to lose 2 protons, we're going to move that way along there. If we're going to lose 2 neutrons, we're going to move that way. So if we've lost 2 protons, we're going to move that way. If we've lost 2 neutrons, we're going to move that way. So the overall movement is in that direction. So elements that exist out here will become more stable by decaying by alpha. Yeah? Elements that exist out here, if they decayed by alpha, they would be becoming less stable. That wouldn't work. It wouldn't happen. You can't get elements decaying to become less stable. They will always decay to become more stable. So they will decay to become closer to this line. Beta, on the other hand, let's see what happened with beta. Oh God, I made a mistake, sorry. Let's go back. Rewind. Go back to here. What are they asking you about beta decay? Remember, beta decay, you get 1 more proton and 1 less neutron. I wrote 1 more neutron, that's completely wrong, sorry. Remember that it's a neutron that decays into a proton and an electron. So you've got 1 less neutron. So what happens with beta decay is we've got 1 less neutron and we've got 1 more proton. So proton number goes up, neutron number goes down, and so this line moves this way towards that line of stability. So elements that exist out here will decay by beta. Does that make sense? Apologies for that. Hopefully you won't remember, you will never forget it, because you'll remember I made a mistake on that one. Don't forget it. If you've made notes or anything, make sure that you've got that. Remember, it's a neutron that turns into a proton and an electron. I'm having a moment. So does that make sense now? Things that decay by alpha are losing protons and neutrons, so they're moving this way. things that decay by beta are gaining protons and losing neutrons, so they're moving that way. So you can see now why elements decay by beta to become more stable, and why some elements decay by alpha to become more stable. So to summarise what we've just done, and I'll leave that graph up there for a minute to see. Let's summarise the whole thing. So we started off by saying that some elements were unstable. They had too many neutrons or too many protons in their nucleus. They weren't on the line of stability, and they were radioactive. We call this radioactive. They're radioactive elements. They give off particles. Okay, and the two types of particles that we talked about today were alpha and beta. And we needed to remember that alpha was a 4-2 helium nucleus and beta was a 0-1 electron. We needed to remember where they came from, how we got them. So beta particularly, we need to remember that we got beta from a neutron breaking down into a proton plus an electron. That's how we got that electron. We needed to remember what happened in terms of the equation. So we need to remember that we start off with the element that they give us, with a Z, and we're going to put, let's do an alpha decay, 4-2 helium, goes to element Y, which is A minus 4, Z minus 2. Next one is beta, remember what we did there, AZ, and we got 0 minus 1 electron, and if we make sure these equations balance, we've got Y with A and we've got Z plus 1. Tells us that we've got one more proton. How do the nuclei change? We said that the alpha particle new nucleus has got 2 less protons and 2 less neutrons. We said that the nucleus following beta decay had 1 more proton. So don't make the mistake that I don't go with what I said before, because I was totally wrong. It had 1 more proton and the same number of neutrons. And we look at this line and we can see why we might get those 2 decays. As I say, all these unstable elements we call radioactive elements. We can't control how many particles come out. When they come out, we can't make any predictions. We say that radioactive decay is random and spontaneous. We cannot make any predictions about what's going on. In the next session, we'll talk a little bit more about the difference between alpha and beta and cover a bit about gamma. Just as an aside, I just want to make sure that this equation is completely balanced. And with beta decay, or beta, we can call this beta minus decay, we also get some energy, and this energy is given out in the form of an anti-neutrino. This thing here is an anti-neutrino. Don't worry about it, but it's what's given out when the neutron breaks down to give that proton and electron. So if that equation were to be completely balanced, you would need to add anti-neutrino to there. Hope that's covered those little bits for you. We'll take a break and then we'll come back and have a look at gamma, and we'll look at what these really are, what happens to these as they're released into the atmosphere or into your body, and we'll look at how dangerous they are and what we use them for in the next session.